Hello friends, welcome to this video on set theory. We are going to see problems on relation in this 7th video on set theory. So let us move on to solving problems on relation. We have seen about the different types of relation, operation on relation in our previous video. I request you to recollect all of them before moving on to these problems. Problem number 1. If R is a relation on the set of positive integers such that the ordered pair A comma B belong to the relation if and only if AB is a perfect square, then we'll have to prove that R is going to be an equivalence relation. So what is that we are going to prove? We are going to prove R is an equivalence relation. An equivalence relation is one which is going to be reflexive in nature. Number 2, it is going to be symmetric in nature. And number 3, it is going to be transitive in nature. Reflexive meaning A comma A has to belong to the set of relation for all A belonging to your set. Symmetric meaning whenever A comma B belongs to the relation, this will imply me B comma A also belongs to the relation. Transitive meaning if A comma B belongs to the relation and your B comma C belongs to the relation, then this will infer that A comma C also belongs to the relation. So before beginning, we need to keep in mind what is the quantity we need to prove. So we need to prove reflexivity, we need to prove it is symmetric, we need to prove transitivity. Then we will be proving that it is an equivalence relation. Now coming to the part, what is going to be the criteria for us? How is the relation now defined? The relation is defined that if it is going to be, the product is going to be a perfect square. So I have the relation R to be defined as A comma B belongs to the relation, that is A is related to B if and only if AB is a perfect square. So we will keep this in mind. So this must be our working rule. So now coming to the part where we prove the reflexivity. Instead of A comma B, I am going to take A comma A. So A is related to A. Is A related to A? This will be true if and only if AB is a perfect square. Now this will imply me A into A is going to be A square, and we know very well A square is a perfect square for all the elements A which I choose from the set of positive integers. Notice that we must not be taking any numbers and proving the relation, because the set of positive integers has infinite number of numbers. We can show that 2 square is a perfect square, 3 square is a perfect square. But what about the n number of quantities which we have not shown the proof for? It is not possible for us to prove all the elements that are perfect square. So in generality, we take it A and B and prove the quantities. So don't take number example and prove problems of this sort. So I have now proved that A square is a perfect square. Therefore the relation R is going to be reflexive in nature. Number 2, let me take the quantity A to be related to B. When I take A to be related to B, this gives me AB is a perfect square. Let me take this perfect square to be something like x square. So now this is a perfect square. If x square is going to be equal to AB, what can I say about B into A? Since A and B are integers, BA will also be the same x square. So if BA is a perfect square, then what can I say? I can say that B is related to A. Where did we begin from? We begin from A is related to B. That is A comma B belongs to the relation. Where we have ended now? We have ended with BA belongs to the relation. B is related to A, and hence we prove that the relation R is going to be symmetric in nature. So two quantities we have proved. The third part is that AB belongs to the relation, BC belongs to the relation, then AC will also belong to the relation. We move on to prove that the third part, namely AB belongs to the relation. So this implies AB is a perfect square. Let me take this AB to be equal to some x square. Now the second criteria is that BC is also belonging to the relation. So BC is also a perfect square. So I have BC to be equal to some other perfect square called as y square. Now AB product BC will be equal to x square into y square. Now let me club this B into B and take it to the opposite side. So the integer A into the integer C, that is AC, will be equal to x square y square divided by b square. So this is nothing but xy by b the whole square. We notice that x, y, b, all of them are integers, and hence this is also a perfect square. Hence what I have proved, that AC is a perfect square. Hence this proves that A, C also belongs to the relation. We started with AB and BC belong to the relation, and now I have AC belonging to the relation. So this says that R is going to be transitive in nature, and hence we have reflexive symmetry and transitivity to be proved for our R. So what can I call R to be? R is an equivalence relation. So that's how we prove the problem. Let us move to the second problem. R is a relation on the set of positive integers is such that A, B belongs to R if and only if A square plus B is even. Prove that R is an equivalence relation. Again, an equivalence relation meaning a reflexive nature, a symmetric nature, and the third one is going to be transitive nature. So let me prove that first one, it is going to be reflexive. What is reflexive? A, A has to be shown to belong to the relation. If I take A, what is the criteria? Let me mark the criteria first. I have A to be related to B if and only if A square plus B is an even number. So this is my relation R. So now I have A to be related to A. So if my A is related to A, then what do I have? A square plus A. And how I can write A square plus A as A into A plus 1. Now if A is going to be any number, A plus 1 is its consecutive integer. And in any two consecutive integers, obviously one of them have to be even number. Hence, I have proved that A related to A, which is A square plus A, is going to be even. So, what is the idea we are using here? The product of two consecutive integers, obviously one of them have to be even, because we have even, odd following in the integers. So I have proved that R is going to be reflexive in nature. Number 2, what we need to prove is symmetric. That is, if A, B belongs to the relation then b comma a also belongs to the relation. What does a comma b belongs to the relation imply to me? That a square plus b is going to be an even number. If addition of two terms have to be even, if addition have two terms have to be even, then both of them have to be odd, or both of them have to be even. Only if both of them are going to be odd, I will have an even number, or if both of them are even, then I will have an even number. In which case, I know that both a and b have to be even, or both a and b have to be odd together. And in which case, I know that b square plus a is also an even number. If b square plus a is an even number, then obviously I can say that b is related to a. Where did we begin the problem with? A is related to b, and we ended with b being related to a. This implies the relation R is going to be symmetric in nature. Moving on to the third one, I have to show transitivity. That is, A related to B, B related to C. I have to show that A is related to C. If A is related to B, then A square plus B is going to be even. In which case, both A and B are both odd or both even. In next case, I have B square plus C is going to be even. Again, in this case, both B and C are odd together, or they are going to be even together. In which case, I can say that A square plus C will also turn out to be even if both A and C are going to be odd together, or they are going to be even together. And hence, if A square plus C is even, I can show that A is related to C. And this shows that the relation R is going to be transitive. If it is transitive, then I have proved that my relation R is reflexive, symmetric, and it is going to be transitive, proving it is going to be an equivalence relation. Let us move on to the last problem. If R is the relation on the set of integers a comma b such that 3a plus 4b is 7n for some integer n, then prove that R is an equivalence relation. Again, we will be proving reflexive nature, a symmetric nature, and the third one to be a transitive nature. Let us note down what is going to be the relation R. A comma b belongs to the relation, that is, A is related to B if and only if 3a plus 4b equal to 7n, and n is an integer. Notice the difference. This is going to be set of integers which can be either positive or negative. What we had in the previous problem was positive integers. So I don't have a negativity here at all. But in this problem, the integers a and b can also be negative in nature. But n again is going to be any integer. So this is going to be my base rule R. Let us start the problem. Now I'll have to show reflexive A related to A. This implies 3A plus 4A, because in place of B I am replacing A. What is 3A plus 4A? It is going to be 7A, which is a multiple of 7. Hence, what do I prove? R is reflexive. Okay. Now let me move to the second part. I know that A is related to B. I need to show that B that related to A. This is to show. Okay. If A is related to B, then I have been given that 3A plus 4B equal to 7n. Let me mark it as equation number 1. My idea is to prove that B related to A. That is 3B plus 4A is a product of 7. This is what I need to show at last. I need 3B. The three integers involved over here are 3, 4, 7. How can I get 3 from 4 and 7? I know that 3B, I can write it as 7B minus 4B using the three numbers over here. Using these three numbers will help me form a relation fast. So I know that 3B is 7B minus 4B. Next, I need a 4A. How to get 4A? I need to get 4 using the remaining two numbers 3 and 7. How will I get 4 using 3 and 7? I know that 4A can be got from 7A minus 3A. 7A minus 3A is my 4A. Now, what I need is the addition of these two numbers. So, add your left hand side, which means it is equivalent to adding your right hand side. Therefore, 3B plus 4A will give me 7B over here, 7A over here, minus 4B minus 3A. Let me combine this minus sign, minus 3A minus 4B. When we take this minus sign outside, I have 3A plus 4B. What is this 3A plus 4B from my equation number 1? My equation number 1 says 3A plus 4B equal to 7n. So this part 3A plus 4B can be replaced with that of 7n. So I have 7B plus 7A minus 7n. Hence, I can show that 3B plus 4A equal to 7 times A plus B minus n. This is a product of 7. Hence, what I have proved? B is related to A. This showing R is symmetric. Hence, we have put the second quantity. Moving on to the third part. A related to B and B related to C. This shows that 3A plus 4B is 7n. This shows that 3B plus 4C equal to 7 times of m, which is some other integer. Mark this as equation number 1, and already this is my equation number 1 from my last slide. So I keep the same numbering and I mark this as equation number 2. So this is my 1 and this is my 2. Now what we need to prove is A is related to C. That is 3A plus 4C is going to be a product of 7. This is to prove. Okay. So let me add my left hand side. When I add my left hand side, I have 3A plus 3B, 4B, that makes it as 7B, and this is a 4C. That gives me 7n plus 7m when I add my right hand side. Left hand side on adding 3a plus 4b plus 3b, 4 plus 3 makes it as 7 plus 4c. And now I want only 3a plus 4c. So this term can be taken to the opposite side. So what will 3a plus 4c be equal to? That will be 7n plus 7m minus 7b. So it is 7 times of n plus m minus b, and which is a product of 7 for sure. So I have proved that A is related to C, proving that R is going to be transitive. Since R was reflexive, symmetric, and transitive, we prove that R is an equivalence relation. I hope these 3 problems could have given you a glimpse on how to solve a problem on equivalence relation. Happy learning. Keep continuing.